Ted. Next 2 weeks, right? So the next week on Tuesday and Thursday, it's going to be a workshop on data modeling, basic modeling and advanced modeling. So if you have any questions on your project or the homework, we will try to resolve that during the workshop. Or you feel free to, you can contact me anytime, right? And the week after that, right? This is the after the next week, it's going to be a presentation, project presentation, where it's similar to the previous presentation, right? You'll have about 10 minutes to present whatever that you have got in your project so far, okay? So the final deadline for the project is due on November 30th. You have about 2 more weeks to work on it, but this is just an initial presentation to uh, to exhibit where you stand on the project, right? I mean, and also to help you if you're having some trouble to contact me after and then after that the course ends. So I think it should all be relieved after that, right? So that's the agenda. Any questions? Yeah.
Yeah. So after the like, what happens between like the presentation and the 30th? Like, what are we?
If you're done with your, I mean, if you have gotten the results and if you have obtained the directed insights and things like that, if you have shown sufficient work in your project, you are free to submit it anytime, even on the 16th. But it's just a time, for people to troubleshoot if they don't have something, or if they want to meet with me on some of these things and trying to get more analysis done on their project, right? I mean, this advanced modeling, it's a very big topic. There are so many things that could be done just within using one data table, right? I mean, you can take some of the variables and then try to do some modeling on it, try to infer the probabilities and things like that. So the time is given for you to work on some of the things if you not have worked on it. So it's just a luxury time that you have.
So the presentation doesn't need to be like a pot, like it doesn't need to.
Yeah, so it doesn't need to be like it need not be the end of your project, right? I mean, it could be the directed or whatever that you have gotten so far. It's just going to be another 6 or 7 slides. I don't want it to be more than that. We don't have sufficient time for it. We have about only 10 minutes for each of them. So if you can wrap up a good summary of what you have been working on your project so far, I think that's the plan that we are having for the project presentation. All right, any questions? Okay, so let's go to more exciting stuff, advanced modeling. Any questions? Have you worked on the previous basic inference and modeling? Any questions on that? You like regression? You have a fair idea? Okay, okay, but you have an idea of what regression can do and what it cannot do, right? Right. I mean, it comes with so many assumptions. Fundamentally, how your data is, first of all, appears and what kind of a model that you apply to the data, right? I mean, so these are two important considerations when working with data sets. I mean, linear regression can be an inference where you can try to model a data set when you know that it has to be kind of a linear. So for instance, let's take a car, right? The number of, the gas you put in there and the miles it takes, right? I mean, you can try to see that it's almost a linear relationship, right? The more gas it is, the more miles it can run, right? So those kinds of problems can be kind of sort of modeled as a linear regression, right? Linear doesn't mean that the linearity in the curve or in the variables, but in the parameters. But there are lots of other places where we cannot model linear, use a linear regression. One of the critical places is that most of these data sets, right, apart from that, it comes with several assumptions. You have lots of categorical variables, and numeric, I mean, rather than continuous variables, right? The residuals, one of the key assumptions for linear regression is that the residuals should be distributed, right, according to a normal distribution, right? But these assumptions are most often invalidated in the real world, right? I mean, and it's also the dichotomous variable. Most of the times you get binary variables, whether there is a mutation or not, right? And also, for instance, we saw that in the mimic data sets, a patient could be admitted into a hospital or not, right, or something like that. Or in Haynes data set, we see that there a person could be diabetic or not diabetic. So in such cases, the linear regression may not really hold, right? There is a nice technique called logistic regression. Have you used it? Logistic regression. I think Sandra gave a presentation on that, right? Logistic regression is a very classic way of dealing with when you have these dichotomous variables, right? And these models are generally captured under what are known as generalized linear model. So it is a very broader framework that covers linear regression, logistic regression, Poisson regression, and depends on what kind of a model that you place on your data set. And these are handled in what are known as generalized linear models. So what generalized linear model in general does is that it applies some transformation to the response variable so that we can model the data in a linear fashion. Okay, so that's why it's called a generalized linear model. And so before we see a specific example, we will actually, I thought it might be a good, I was like trying to find out a good video for explaining logistic regression, and I thought this was really good. So let's look at this video on, I think I'm not really sure whether we will have the sound card here. This is a big problem. Let's see. I might. Oh,
Think of what could drive customers' preferences to buy a certain product. Amongst the independent variables we could find, we could have continuous ones such as age or the person's income or a person's height, which is important for clothing. All these have numerical values. We could also have categorical variables that determine a customer's product preference, for instance, gender, city, or ethnicity. And we had learned that we could use dummy variables to represent these. On the other hand, we could also have various forms of dependent variables. For example, we could quantify with numbers how much does a customer spend or how much time does a customer spend at a store. However, a more simpler question could be if a customer buys a product or not, which is a categorical variable with two potential outcomes. For these kind of variables, we will be using dummies. Let's look at some examples of questions with binary outcomes. At a bank, for instance, we could wonder if a person is worth of credit or not, and should we give that person a loan or not. If you're looking at individual transactions, we could use a binary outcome to model if that particular transaction is a legal or a fraudulent transaction. In the context of schools, a yes-no question could be if a particular student is admitted or not into the school. In the context of politics, we could assess if this person will vote against or in favor of a particular law. Finally, coming back to the retail context, a binary variable could mean that a customer bought a product or did not buy a product. So, how could we represent binary outcomes? Recall, these are variables that only have two potential values, usually indicating if an observation belongs to a certain category or has satisfied some particular attribute. It's going to be a yes-no question. Similar to how we did with independent variables, we can create a dummy variable that is going to be equal to 1 if the answer to our question is a yes, and a 0 otherwise. Note that if we coded our dependent variable the other way around, the coefficients are going to have the same magnitudes but the opposite signs. How come? Well, whatever helps me, for example, buy a product will have the exact opposite effect in helping me not buy that product. And thus we're going to have the opposite sign for that attribute. The data we will be using in this example is a set of 1,000 random customers from a given city, and we want to know what determines their likelihood or decision to subscribe to a particular magazine. Our dependent variable, naturally, is going to be an indicator variable that tells us if the customer has subscribed to the magazine or not. It will have a 1 if the subscription took place and a 0 otherwise. We also have access to some demographic information that could influence a customer's likelihood of subscribing to the magazine, for instance, age. And in fact, in this video, we will only focus on this particular attribute of a customer. We could also have other attributes such as gender, but we will not rely on them on this video. If we think about the problem, we don't see too many reasons why we could not use a linear model. Because aside from being binary, there's really nothing else special about this binary dependent variable. In fact, if we want to change this binary variable from a 0 to a 1, we are changing its value to a higher one, and thus anything that increases the value of y should favor the likelihood of a customer subscribing to the magazine. So we could run a simple linear regression model that looks as the one shown, where we have subscribed the binary dependent variable as dependent variable and age as our only regressor. The regression output in a statistical package, in this case Gretel, shows us the coefficient for the intercept and the slope. So our estimated model is subscribe equals minus 1.7 plus 0.064 times age. And what does this result mean? If we recall that our dependent variable is binary, it's a 0 or a 1, and we want to make it grow from 0 to 1, this is very closely tied to trying to increase the probability of a customer buying, where the probability of subscribing equals 1 is the likelihood of a customer subscribing to the magazine. Let's denote for simplicity this probability as P, and then we can rewrite the model as the probability of subscribing equals 1, or P, is minus 1.7 plus 0.064 times age. So since this is the slope of our model, we can simply take the coefficient of age and make the following assertion. Every additional year of age increases the probability of subscription by 6.4%. And this makes a lot of sense. Now let's check if we can use this to forecast probabilities of customers with given ages. Recall that probabilities are bounded and they have to be between 0 and 1. Moreover, also note that the range of age in our dataset goes from 20 to 55. That is, the youngest customer in the dataset has 20 years old and the oldest one has 55. Since it only makes sense to develop forecasts for observations similar to the ones we have in our data, then we can assume that computing the estimated probability of a 35-year-old person subscribing is very easy. What we must do is simply plug in the 35, and we find that the estimated probability of a 35-year-old person subscribing is 0.54. So far, so good. But what about people with 25 or 45 years of age? Given the range of age, this should work just as well. However, if we plug in 25, we find that the probability that this customer buys is estimated to be minus 0.09. And this cannot be correct since a probability cannot have a negative value. Similarly, if we plug in the 45, we end up with a number of 1.2, which is greater than 1, again an invalid value for a probability. This becomes more clear if we plot what we're having. In this plot, you observe the bounds of probabilities that should go from 0 to 1. And note that when customers are young, say below 26 years of age or so, the estimated probabilities are negative. Meanwhile, if the customer has more than 43 or 44 years of age, the probabilities are greater than 1. This model is just not working. How could we fix this? One option is to artificially cap the linear model and say, whenever the estimated probability is below a 0, make it a 0, and whenever the estimated probability is above 1, make it a 1. And this would give us a spline function as the one showed with those breaks in the function, but this is too engineered, way too custom to be a standard approach. Could we do something better? And let's think, what should we do to fix this? Once again, note that probabilities should be between 0 and 1. And we know that the probability will be a function of age, however, the linear function did not work for us. So what conditions should this function satisfy to always produce reasonable forecast for the probability? I will give you a few seconds to think about this. Well, there are two main attributes that must be satisfied. One is that the probability must always be positive, and second, that it must be less than 1. So let's now try to develop a new function that satisfies these two criteria. And we're going to do it step by step. First, let's ensure that we have a positive number. And what functions could give out positive numbers? You can think of the absolute value of a number as always positive. The squared version of any number is always positive as well. And an alternative to this is an exponential form, whereby the exponent of beta 0 plus beta 1 times age, which is the same as saying e powered to beta 0 plus beta 1 times age, is always going to be positive. You can check it in Excel or in some other software. It's always going to be positive. However, it sometimes will be greater than 1. So we need something else to satisfy the second criteria, that the probability is less or equal than 1. And if you think about proportions, any given number divided by a number that is just slightly greater than it will give us a number smaller than 1. So why not do the same? Why not use the expression we had before and divide it by something that is slightly larger? How much? Well, just 1 unit larger. We have the same expression above and below, but in the denominator we have a plus 1. Note that we could have added any small value or large value, an epsilon for that matter, and the condition of having a value less than 1 would still be satisfied. However, we use 1 for reasons that will become clear shortly. Now, even though we have this more complex expression, the linear thinking is not completely gone. If we do some algebra, the previous expression can be written as follows. We have the log of p over 1 minus p being the result of the prior expression, is equal to a linear function of age that looks just like the linear simple regression models we had before. So even though the probability of a customer subscribing is not a linear function of age, we can perform a simple transformation on it such that it is now a linear function of age. The above equation is the one used in logistic regressions. And let me show you the output of a logistic regression in Gretel. We can see that we have the coefficient for the intercept and the slope, the beta 0 and the beta 1. But how we interpret these coefficients is different. We will discuss the interpretation of the coefficients in another video. For now, let's simply note that the model we estimated, given that our dependent variable is the log of p over 1 minus p, is minus 26.52 plus 0.78 times age. Or if we do the algebra again and write this in terms of the probability, we have that p is equal to that expression. And note that all what I'm doing is rewriting the expression, but substituting the beta 0s and beta 1s for the corresponding coefficients that came out of the regression output. If we now plot the probability against age using this expression, this is what we find. And note that the probability is no longer below 0 or above 1. In fact, as customers grow older, the probability asymptotically gets closer to 1. And as customers grow younger, the function is asymptotically closer to 0, but never below 0 or above 1. This is the plot of a logistic model. Thank you very much.
All right. So basically we have this log, right? I mean, instead of just viewing it as a regular regression, we are now taking the values and interpreting as a log, right? So we will apply this to one of the data sets. So in the previous Haynes data set, right, we saw there were already two clusters in there if we log transform A1C and UACR variables. You remember there was, when we log transformed it, we saw there are two clusters, right? So here, with people with diabetes and this. Initially, when I was doing this, I was thinking that this cluster was people with diabetes or something like that, or this cluster represented with no diabetes. But then only when I plotted the class variables, I could see that that's not the case, and these people are non-diabetic people. So within even the non-diabetic people, we have two classes. So one of the things that I was thinking is that why don't we just apply a logistic regression on this, right? So I was thinking we could separate these two clusters. So in a set of all non-diabetic people, we can call the lower cluster as 0, right, and the upper cluster as 1. So we see that there is when you have -2 as a line of separation between these two clusters, right? So we can heuristically take the log of UACR less than or equal to 0 as a lower cluster and the 1 as an upper cluster, right? I mean, we now manually do this, but there are more efficient ways of doing this using k-means and stuff like that, okay? So we will, that's in the machine learning algorithms, and that comes next semester. But before, right now, we will just stick on to this. And we can now ask the question out of these the creatinine or U-albumin variables that make these ratio, right? UACR stands for urine albumin creatinine ratio, right? Which of these two variables distinguish these two clusters? So we now have the ratio and we want to see which of these two variables distinguish these clusters. And this can be done through logistic regression, right? So, but before that, we need to extract this data using the data transformation technique. So what I'm doing here is I'm taking the data set and I'm filtering it for people who don't have diabetes, and then making this cluster, forming a new variable called cluster, right? So this would be a very useful technique. You can use if else inside the mutate, okay? So that would allow you to actually form a new variable. For instance, here I'm forming a cluster. I'm saying that if log of USCR is less than -2, then substitute it with 0, otherwise it's a cluster 1, right? And you can in fact put an if else inside this if else too. So if you want to have several categories, you can do that, okay? So this is a very useful function, mutate plus if else, that can create new variables. Okay, and then I'm selecting everything except all the factor variables. So I'm selecting everything except key, gender, age group, etc., etc. Right now I can plot it to see that if I have captured that, yes, I mean this is cluster 2 and this is cluster 1. So I just wanted to capture these two variables, right? Now we can perform the logistic regression where the predictor variable, right, will be the creatinine variable, and we can also perform a logistic regression with albumin variable. So it's important to know what variable do you choose for logistic regression, right? I mean, you can choose every variable and these values may not be really significant, or instead you can focus on these two variables and then try to do a logistic. So it's all you know, the feature selection is one of the critical problems actually in machine learning. But anyway, so what I'm here doing is taking this and then forming applying this general linear model known as GLM, right? The response variable is cluster and the predictor variable is U, the creatinine ratio, and then GLM comes with a family, okay? You don't necessarily need to give this link. It's by default it's a logistic regression, so it will take the link as logit, okay? So you can make this generalized linear model, apply this generalized linear model, and then use a summary to spit out the coefficients, right? And similarly, you can do it for the U-albumin ratio. So when you do this, I get this result that gives me some deviance residuals and coefficients, which is a critical values here, the intercept and the U-creatinine ratio, right? So this is for the U-creatinine ratio, and it says that this is a significant variable in here, the predictor variable here, compared to U-albumin ratio, right? I don't have any degrees of significance associated with U-albumin ratio, right? So the result of the summary can be interpreted as follows: the intercept, right? This intercept can be interpreted as a log odds of a patient with U-creatinine value of 0 being in the class where UACR is less than 2, that is in cluster 0. So that's the intercept. And the coefficient is interpreted as a log odds of 1 unit increase in the U-creatinine variable, right? So the odds can be calculated by exponentiating the values, just like we saw in the video, right? I mean, this is a log odds, right? You can exponent, and you get for the U-creatinine it's 1.02, which means that we expect to see about 2% increase in the odds of being in cluster 0. So that's the interpretation you can give for the eucreatinine, and the negative intercept means that the cluster are less likely separated by eualbumin, right? So with this, and coupled with the statistically significant coefficient, we can say that eucreatinine distinguishes the cluster better than these two. Okay, so which is actually, I mean, it is more, the cluster is decided by the eucreatinine ratio, and this puts us into more questions on why that is causing this kind of a cluster and things like that. So which we can analyze later, right? So as a homework, you can perform the logistic regression and versus diabetic versus non-diabetic population, and report which variables distinguish the population. You can use all the variables to do a regression, so it doesn't matter for this exercise at least, right? And report what are all the variables that distinguish the two populations, right?
So here you use the U creatine and the U albumin because the UACR was a ratio of both.
Yes, but for a predictor variable, I could have as well used as many variables as I wanted to. I need not have restricted to eucreatinine or eualbumin, but then you will get a totally different result in which you will not find anything significant at all. You can try that, yeah.
And then so here U creatine is like the more, I guess, the factor. So if we were to plot the log of A1C and the log of U creatine instead of the UACR, then we would still see different clusters.
Yes, well, I don't know how far the A1C. Yes, you're right, in the sense that it represents the cluster better than the albumin ratio.
Okay. So like the next step could be to do that and then other features to see it.
Right, for this, but you can as well do it on diabetic and non-diabetic people. I mean, and for your project, right, take any of the variables, it doesn't matter, and then you can try to, categorical variables, and then try to do this logistic regression on it, right?
When you have the code that had like the negative or the minus, is that the same as saying you're like adjusting for those values?
No, so I mean the negative, that's a very good question, because the negative coefficients in logistic regression are really hard to interpret. So in general, it may not really mean anything statistically or meaningfully significant. So while the positive coefficients do mean something. So I think that is a very critical point to have this. When you have some negative values, you really cannot distinguish things in logistic regression. Okay.
Is your Y variable dichotomous or no for the diabetes? Because there were 3 categories, right?
Yeah, yes, it's between diabetes and non-diabetes, so you can leave the.
So it's not a polytomous, like logistic.
No. Actually, you can use logistic regression for more than
Yeah.
2 variables, binary variables. But
Okay.
for the exercise, you can just restrict to 2 variables.
Okay. If we were to plot more than one category in our Y, how would we do that?
In your Y, if you are having 2, or what's that?
Or like if we were to actually make a regression of a Y dependent variable that has more than 2 categories.
But you can still plot it.
Still with the same.
Yeah. You can still plot it, and you can have the same formula, right?
Okay.
I mean, you can have that generalized linear. All right. So these are all right. I mean, so far we have just seen how these work from a more a modeling point of view, but you need to know the mechanics of how these are all done actually at the end of the day, right? I mean, right now, yeah, you have a model and stuff like that, right? But what's behind the hood? How does these work? Algorithms work, right? So GLMs are usually solved using the method of maximum likelihood. Okay, so there are 2 essential methods that we can try to use for solving such models. One is the ordinary least squares, in which case actually the ordinary least squares and maximum likelihood will be the same for linear regression. But for nonlinear regression, like this one, which comes under the generalized linear regression, linear model, these are solved by the method of maximum likelihood. Okay, so which in turn uses optimization techniques like gradient descent to find the parameters. So who has heard about all these maximum likelihood here? You? Okay. So how do you know how, so it's a maximum, like that's what we are going to see, how maximum likelihood is applied to a data set, okay. Likelihood is a probability of observing a data given a model. Okay, so let's say that in the univariate case, there is only one variable, right? Let's say that we have a set of data and a model parameter. You have a model parameter. Then the likelihood function is given as a probability of observing the data given the model, right? So that's the likelihood function, and it's written like this, right? So if our observations are independent and identically distributed, right? Here, for instance, patients are identically independent, right? And they could come from the same distribution. We can treat this product as a product of the probabilities, right? You can separate it them because they are independent, right? So the and is now you can write it as a product of the probabilities. So let's look at some concrete example here. Okay, so suppose that we draw 200 people in random and identify their gender, right? So I took like 200 people from the Haynes data set with gender, and then I wanted to see the number of females in the population, right? So when you do that, see that here there are about 118 females in the population out of these 200, right? So the first thing is to assume that we know that the proportion of males and females in the population. Let's say that we know that. We ask ourselves how likely we could have drawn this, information if we are right about the proportion. So let's call the proportion of females as gamma in this case. Okay. Now here there are only two categories, male and female, right? And each of them are sampled independently, right? Then we can calculate the product of the probability. So it will be gamma if the observation is a female, and 1 minus gamma if the observation is a male, right? And we can take the product of their probabilities, right? And we can use this equation to calculate the probabilities of getting a specific sequence. What is a probability of getting this sequence, right? So I'm computing this probability, right? If it is a female, I give it as 0.5, assuming that they are equally distributed, and I can take the likelihood of the probabilities, right? So once I do that, I can see that what is the probability of observing when men and women are equally distributed is very small, right? So this observation, when they are equally distributed, right? Let's say that if men are overrepresented in the population, I can assign the probability of 0.2 for females and 0.8 for males, and then compute this probability, right? So, and then you will have the associated probability for these in this case, right? So in general, we can generalize this as a function of gamma and graph the likelihood as a function, right? So when you do that, so what I'm doing here is taking the function gamma and I'm plotting the probabilities. When you do that, you get this distribution, right? So here the gamma, you could assign any probability, and what is the likelihood is just the product of the probabilities here, right? The product of what you take. Now, the same idea can be used for the proportion with diabetes instead of males and females. So here I sampled 200 people with diabetes, and we can have the probability distribution for this. Here you have this kind of a curve, right? Instead of male and female was distributed around this region, right? Now, this is the idea, right? The likelihood is not a probability function, but it is a probability given the model, right? It can be used to identify the parameters of the underlying population. This parameter is called the maximum likelihood estimate, okay? So it is the estimate of the parameter in your model. So for instance, in our regression, logistic regression, we had some model, right? Beta naught and beta 1 coefficient, and those will be the parameters. And we can generate based on the logistic curve, you can have a maximum likelihood of that curve for that model, right? Exponential, whatever, you can have the curve for that model, right? So thus the maximum likelihood estimate is the value of the parameters given that maximizes the likelihood of observing that, right? So you can mathematically, it is defined as maximum of gamma, the likelihood estimate. And there is an ARC program to do is it's called optimize, and you have functions of gamma, and you can find the likelihood estimate of that. So if you do that, then it solves it as 0.58 for the male and female example, right? Similarly, we can there is also we can do it for the this is the estimate for the maximum. So for the male and female distribution, this optimized function, we will see about the optimization function, but essentially it gives a maximum as 0.58, and this is the diabetes population, right? The diabetes population, it's giving us 0.09. We can solve this for the objective function. So all this means is this following. This, you had this curve, right? So this is at 0.9, it reaches the maximum. So it's trying to optimize and trying to find out where this curve reaches the maximum. Okay, that is the maximum likelihood estimate for the given probabilistic, for the given model, right? So what this means is that in the case of males and females, the maximum happens at 0.59, suggesting there are 59% of females in the population, right? And this is unlike diabetes where we saw the maximum is 9%. Actually, the official estimate is about 9.3. So we are pretty much close actually, looking at this example. So maximum likelihood can be extremely useful to determine the parameters of the underlying distribution. And determining maximum likelihood, actually it becomes, to use the product of the functions is very difficult, right? So that's why we need is cost function. Well, the cost functions are this. Cost functions are negative log of the probability, okay? So instead of maximizing the likelihood, we can minimize this cost function, okay? So the log is additive. So it will convert the multiplicative probabilities into additive probabilities. So that, and also there is a good reason for using the log, okay? I found this one of the classic videos. Actually, it's very good. So let's watch this. Why?
Imagine two machines. They both output messages from an alphabet of A, B, C, or D. Machine 1 generates each symbol randomly. They all occur 25% of the time. While machine 2 generates symbols according to the following probabilities. Now, which machine is producing more information? Claude Shannon cleverly rephrased the question. If you had to predict the next symbol from each machine, what is the minimum number of yes or no questions you would expect to ask? Let's look at machine 1. The most efficient way is to pose a question which divides the possibilities in half. For example, our first question, we could ask if it is any two symbols, such as, is it A or B? Since there is a 50% chance of A or B and a 50% chance of C or D. After getting the answer, we can eliminate half of the possibilities, and we will be left with two symbols, both equally likely. So we simply pick one, such as, is it A? And after this second question, we will have correctly identified the symbol. So we can say the uncertainty of machine 1 is 2 questions per symbol. Now, what about machine 2? As with machine 1, we could ask 2 questions to determine the next symbol. However, this time, the probability of each symbol is different, so we can ask our questions differently. Here, A has a 50% chance of occurring, and all other letters add to 50%. So we could start by asking, is it A? If it is A, we are done. Only one question in this case. Otherwise, we are left with 2 equal outcomes, D or B and C. So we could ask, is it D? If yes, we are done with 2 questions. Otherwise, we have to ask a third question to identify which of the last 2 symbols it is. On average, how many questions do you expect to ask to determine a symbol from machine 2? And this can be explained nicely with an analogy. Let's assume instead we want to build machine 1 and machine 2. And we can generate symbols by bouncing a disk off a peg into one of two equally likely directions. Based on which way it falls, we can generate a symbol. So with machine 1, we need to add a second level, or a second bounce, so that we have 2 bounces, which lead to 4 equally likely outcomes. And based on where the disk lands, we output A, B, C, or D. Now machine 2. In this case, the first bounce leads to either an A, which occurs 50% of the time, or else we lead to a second bounce, which then can either output a D, which occurs 25% of the time, or else it leads to a third bounce, which then leads to either B or C, 12.5% of the time. So now we just take a weighted average as follows. The expected number of bounces is the probability of symbol A times 1 bounce, plus the probability of B times 3 bounces, plus the probability of C times 3 bounces, plus the probability of D times 2 bounces, and this works out to 1.75 bounces. Now notice the connection between yes or no questions and fair bounces. The expected number of questions is equal to the expected number of bounces. So machine 1 requires 2 bounces to generate a symbol, while guessing an unknown symbol requires 2 questions. Machine 2 requires 1.75 bounces. We need to ask 1.75 questions on average, meaning if we need to guess 100 symbols from both machines, we can expect to ask 200 questions for machine 1 and 175 questions for machine 2. So this means that machine 2 is producing less information because there is less uncertainty or surprise about its output, and that's it. Claude Shannon calls this measure of average uncertainty entropy, and he uses the letter H to represent it. And the unit of entropy Shannon chooses is based on the uncertainty of a fair coin flip, and he calls this the bit, which is equivalent to a fair bounce. And we can arrive at the same result using our bounce analogy. Entropy, or H, is the summation for each symbol of the probability of that symbol times the number of bounces. Now, the difference is how do we express number of bounces in a more general way? And as we've seen, number of bounces depends how far down the tree we are. And we can simplify this by saying that the number of bounces equals the logarithm base 2 of the number of outcomes at that level. And the number of outcomes at a level is also based on the probability, where the number of outcomes at a level equals 1 divided by the probability of that outcome. Number of bounces actually equals the logarithm base 2 of 1 over the probability of that symbol, which gives us our final equation. Entropy, or H, is the summation for each symbol of the probability of that symbol times the logarithm base 2 of 1 over the probability of that symbol. And Shannon writes this slightly different, which just inverts the expression inside the logarithm, which causes us to add a negative, though both formulas give the same result. So let's summarize. Entropy is maximum when all outcomes are equally likely. Anytime you move away from equally likely outcomes or introduce predictability, the entropy must go down. Now, the fundamental idea is that if the entropy of an information source drops, that means we can ask fewer questions to guess the outcome. And thanks to Shannon, the bit, which is the unit of entropy, is adopted as our quantitative measure of information, or measure of surprise.
All right, so basically that's how we are doing here. We are taking the maximum likelihood principle and then forming the negative log likelihood, which is a measure of information, as what we want to minimize, right? We want to minimize the cost function, right? The entropy in the information, right? So that's what we are doing here. So there are other cost functions in areas such as motion planning and traveling salesman, and there are several other things. For this, we will just use this cost function as negative log likelihood, right? And with this, we can formulate the cost for the given parameterization, right? So you have this cost. We can make try to find the cost for this, the male and female thing, right? I mean, this is the negative log likelihood of that maximum likelihood that we had. And similarly for the diabetes population, we have this is the cost function, right, corresponding to the data that we had. All right. So the maximum likelihood function is a minimum of the cost function, right? And so to maximize that function, we need to minimize this cost function. And that is why we use so many optimization techniques to find this minimum. Okay, so there is lots of optimization techniques to find this minimum. So how do you go about in finding the minimum? You have a function. So one of the simplest ways is to grid search, right? So what we do is, in this approach, we break the data into lots of small intervals and try to estimate the cost function on those intervals. It's a grid because it can be visualized, right? Something like this. So you have this curve and you can evaluate the cost function at these points, right? So let's go back to the original logistic regression. You might have a function that you will write and we have to minimize it, right? So the cost function would something like that, and then we can evaluate and estimate the cost function, to estimate those parameters beta naught and beta in that, right? So it's, and also for this, this can be implemented for the diabetes population like this, right? I mean, so what we are trying to do is here taking the sequence and incrementing, and then we can try to estimate the cost. This is a supply is estimating the cost. You can just apply to the cost function, and we can try to see. And the value is 0.09. It's really good, right? So it's almost the same, right? We have that. So why is this approach bad? Before I tell you the answer, why is the grid search could be potentially bad? Because think about it. So it's the computation. We have just one parameter, but what about if you have two parameters, right? So, and also it depends on the precision of values. So if we have a parameter and if you just, let's have a 3 parameter, right, the cost is going to be really huge, right? I mean, even this is like a million, right? I mean, so even for a small precision, it's determined, it has a bottleneck of of the grid that you construct, right? I mean, so we can do something smarter by doing what is known as a gradient descent. So the gradient descent, what we do is we slide along the curve. Instead of taking a grid, we slide along the curve, and that is mathematically described by this. What it means is that you take the gradient, which is the how you slide, I mean the direction in which you slide along the gradient, and how much you slide along the gradient, right? That is the gradient. That's this, and this is called as a learning rate, okay, in a more machine learning parlance. But so that's in a single variable, right? Delta C is nothing but a derivative. So for instance, in the diabetic population, right, it is extremely easy to compute this. So what we had 200 people minus this diabetes count, and also this, right? It has a log of that, right? So the logarithm of the cost function, right? Log of, what is the derivative of log x? 1 over x, right? Have you studied calculus before? Okay. The derivative of logarithm is 1 over x, right? What is the derivative of sine x? Cosine. Okay, fine. What is the derivative of 1 over x? Yeah. So here the cost function is logarithm, right? The logarithm is 1 over x. So that's why you have this cost function. If you take the derivative, you'll see this. And so once we have this, we can do a gradient descent, right? So we need 3 parameters, the parameter called theta here, and we need an initialized parameter. We have to initialize a parameter, and so and also the learning rate, right, that is given by theta, and the precision, right? And so we can apply this function, and the prior cost is this, and then so we can plot these and see that it converges to 0.9. Okay, so that's fine. And in fact, we can see this convergence. So it started with here, right? And the second iteration, it went here, etc., etc. And after this point, it can't go any further because this is the minimum, right? We have a threshold for it, right? So we have the threshold saying that, oh, if it is if the new cost minus the old cost is lesser than the threshold, then stop the iteration, else continue, right? So this loop takes care of the convergence, and you finally end up here, right? That's 0.9, right? But several times we will not have an analytic form of the derivative, right? We might have a difficult model, right? And so we can still apply the numerical approximation for a derivative, which is given by this, right? So we can use this, and you can also see that this also gives almost the same result. So that's just a sanity check, right? Superb, fine. Multivariable modeling, it's similar. Just like we saw in a single variable, we can do a multivariable. And in general, usually in the problems, you will have lots of things. Even in the logistic regression, you have two parameters in there, right? So let's consider an example here. I took the glucose test and hemoglobin test, right? A1C are the two common tests to identify diabetes. And if a person is having glucose levels greater than 126, or A1C levels, the hemoglobin levels are greater than 6.5, they are diagnosed diabetic, right? Otherwise, they are not diagnosed diabetic. And let's say that we want to estimate the probability of someone being diabetic given these two variables, okay? So we can define the conditional probability, saying that the probability of someone being diabetic given the hemoglobin is greater than 6.5, I denote it by a parameter, okay? And the probability of someone being a diabetic given the glucose parameter is greater than 126 is theta of GLU. Okay, so I have these two parameters. Now, from the laws of probability, we have, if they are less than 6.5 or 126, we don't know, it's just P, right? If they are greater, the A1C is greater than 6.5, we have this, right? If the glucose is greater than 126, this is the probability of having a glucose, right? What if both have, it's both 6.5 and glucose is 126? What happens then? So in that case, their diabetes could be contributed by the hemoglobin or by glucose, right? We do not know. And that's why we have these negative A1C and glucose here, okay, that counteracts. It's just a probability of A union B is probability of A plus probability of B minus probability of A intersection B, right?
That's not an interaction or anything like that, right?
What's that?
It's an interaction, measuring interaction?
Yes,
okay.
Exactly. So that measures the interaction variable, right? So we have these two hidden variables, A1C and glucose, that we need to identify. And also we have the variable P that defines the population that is unexplained, right? So this can be computed directly from the observation. So what is P here? The P is A1C less than 6.5 and glucose less than 1.126, right? So we can try to find, so we can form this, right, of A1C greater than 6.5, and then we can select these two variables and have this here, right? And also we can have a data matrix corresponding to the observation of how we determine P from here, right? If A1C is false and glucose is also false, right? And that if they have diabetes, then we can try to find the proportion of these, right? And so from this, we see that that probability is 0.2, right? Unexplained probability. So if people they don't have diabetes, they don't have the glucose levels are less than 126, and their hemoglobin levels are 6.5. You try to find who all have diabetes in there, and then try to see what's the proportion they represent in the population. That is unexplained by both glucose and the hemoglobin, right? And then we can define the maximum likelihood that takes into consideration the two types of the same kind of I mean, it's similar to one variable, right? I mean, it does not, it's a similar here where we have these predicted variables, diabetes variables, and I'm just applying the formula here, right? We have these two, and then here is the interaction term, probability of A plus probability of B minus probability of A times B, right? And then I'm forming likelihood explained and likelihood unexplained. And then I'm forming the cost function, right? So this is the cost function. Now, we can now see the cost functions looks like by looking at the various probabilities. So what I'm trying to do is that I'm generating just like how we did, right? For the varying the cost functions, I'm trying to see what is the probability by varying the probability of diabetes. So this is just like how we did for the single variable. I'm just plotting it in the two variables and then making it as a scale, right? Any questions so far? No? It's all clear? Okay. So the cost is minimized somewhere around 0.6 and 0.5. Okay, if you look at it, the cost is minimized somewhere around 0.6 and 0.5, but we don't know exactly where, right? So we hope our optimization technique will give these values of the hidden variables. Okay, so we have these variables. It's similar to what the one variable is. The gradient is given by this. In our particular case, this is the variable, right? Delta C by A1C and dou C by the glucose variable, right? And this can be approximated. And so we have the approximation just like what we did for the single variable, right? We have the two, instead of computing the analytic derivative, we can have the approximation here, and we can now see how the derivative works. So if it is, so we have to start with the point, and if we start with the point, it's going to come in this direction. If you are going to start here, it's going to come in this direction. If you are going to start here, it's going to come in this direction, right? So we can see how the gradient descent actually works, right? I mean, and also we can, we need to initialize where we start, right? And let's give some of these parameters and plot how these work, right? So here, so it started here and then slowly converts down to here, right? And this can be, the value can be exactly obtained, and what we obtained is theta of A1C, right? It's 0.62, and the glucose variable is 0.48, right? So this means that the probability of observing someone with diabetes given A1C is 62%, and the probability given glucose is 49%, and both these values give you a probability of 81%. Okay, so it's best to use both of these just instead of using one of these. Okay, so that's the inference you can get this. Okay, now it's your turn. After that, you have to find out, you have to use the analysis of finding someone diabetic using HDL and LDL estimate instead of A1C and glucose. Okay, so just change the variables. It should be straightforward. If you get the idea, you can apply this to your data set and try to do lots of things. So there are already, and in fact you don't have to do all these things. There are lots of these optimization techniques are available. Okay, you can use the function called optim. So it takes into only it needs only two inputs. One is the initial guess and the cost function, right? So once you give this cost function, it's going to print out the optimization value. I mean, all these things that we did can be just done in one line using this optim function, right? And also this kind of varies from what we have, right? I mean, we had about this gives you we had about, this is 65 and and 38. We had, I think, 62 and 48. It varies when you use this, but there could be so many problems. I mean, there could we will go over some of the problems in such approaches. Okay, but the differences could be attributed to what are known as local minima. Okay, so have you heard of these local minima problems in optimization, right? So it's one of the trickiest problems, but yeah. So it uses Nelder-Mead method. Okay, so there are so many options there and things like that. And the gradient descent too will suffer from these problems, but we'll see shortly what these problems are. But there are other optimization algorithms which can be used. One is the BGFS algorithm. So instead of just using optim, we just specify method equal to BGFS and we print out those values, and it's giving the same value here too. And also you can use, if we already know the gradient analytically, we can use that here. GR equal to gradient, and it's going to give you that. So these are some of the options. You can check out all these things in this algorithm. And finally, we have another algorithm, right, which is called which you can specify the constraints. Here we know the probabilities are bounded by 0.9 and 0 and 1, right? So you can constrain optimization. It's a huge area of research, and you can specify the constraints, and probably that will help you to get your answers easier, right? All right, now let's do some big data modeling, stochastic gradient descent. One of the key ideas here, right, in this is that at every point of iteration, you have to evaluate the cost function. So for instance, in the case of Haynes, it was okay, manageable. It was only 1,000 observations, right? But in case you have millions of observations in mimic data set, right, and things like that, like there is a huge image repository called ImageNet. They have like 42 million or something like that data points. So how will you do such things? How will you do big data analysis on these optimization techniques? What we can do is what is known as a stochastic gradient descent. It's a simple observation. The thing is that the cost of errors on one observation is independent of any other observation. Okay, so if there is a patient, right, one patient is independent from the other patient. So the cost that he incurs for his probability is independent from what the other person incurs as a probability, right? So what we can do is that we can approximate the gradient by only choosing some number of observations. That's the key idea here. So instead of doing over 1,000, I'm just doing over 100 observations. Evaluating the gradient for 100 observations. So the only thing that I would have to introduce is another parameter called the n parameter. That's the number of iterations. Okay, so this gives almost the same value here, 0.63 and 0.44. I mean, this is really close to what we estimated by the multiple gradient descent, right? And in fact, you can plot these and see how the convergence. So this is the first one that converges, the purple, and then yellow, and then blue. I have given some various colors in here to see the iteration, and it just needed 3 iterations actually. You know, if you look at if you zoom in, it shows a different color here. So all it needed is a 3 iterations instead of if you choose 1,000 observations, right? I mean, it's going to do everything, right? So the stochastic gradient descent will save us lots of things if we have lots of data sets, right? I mean, lots of observations in the data set. In parallel frameworks, so we know here, right, A1C is greater than or equal to 6.5 and glucose is 126. What if we don't know? What can you do about it? But note that this is easily parallelizable, right? You can take 2 and evaluate it on a cluster, right? I mean, this perfectly fits with the MapReduce framework and things like that, right? So you don't have to really compute everything, right? I mean, on one node, right? You can take a number, 100, glucose is 100, and A1C as 4.5, and evaluate the cost on one cluster, and try to find the minimum out of all the things that you get that optimizes the value, right? So stochastic gradient descent can be used to determine for such pair, and eventually you can choose the minimum of the minimums. Okay, so if you have large data sets, you can do it using MapReduce or other frameworks by using this. I mean, I'm not going to pain you in doing this, but this will be a big project if you want to take it on later. All right. So why we had a difference, and that's because of some of these. Look, you have this cost function, right? You have some function, and let's compute. I made up this function, and if you do the minimum of this function, right, it gives you gradient descent gives you minus 1.29. Fine. Are we done here? Let's look at it. Okay. So what do we have here? It gave us minus 1.29. Is that the minimum of this function? This one, right? So what's the problem here? There are two minimas here. One is called a global minimum and the other is called a local minimum. Okay. If a point is a global minimum, if that's the lowest value for all values in the domain, okay. It's a local minimum if there is a lowest value among some range in the domain of the around that point, right? So this is a local minimum and this is a global minimum. So in general, gradient descent values, they are highly sensitive to where you started. So for instance, here I started the gradient, the initial value is minus 2.5, right? So that's the initial value that I gave. And so it converged into this. But have I started some value here, it would have given the global minimum. Okay, so this is a very extremely important problem. And gradient descent doesn't give any claims to global optimal results. The result could be locally optimal or even suboptimal, right? But are we out of luck? Actually, not really, because there are some classes of functions, okay, where the global minimum and the local minimum coincide, and these are called convex functions. Okay, so loosely speaking, a convex function is a function if we, for every line segment that you draw, right, if you draw a line segment, the graph of the function should lie below it. Okay, so that's called a convex function. So here this is not a convex function, right? So the graph is lying above it, right? But think about it, for a convex function, if this line segment has to lie below it, there has to be only one local, global and local minimum, right? So that's the idea of convex function, right? And the whole area is called convex optimization. And if you have a convex function, if you're modeling a function and that is convex, life is more easier. It's super nice. But in general, we may not have it, right? I mean, there could be so lots of non-convex functions, and this is a big area of research, and there is non-convex optimization and global optimization and several other things, okay? But take it from me that if you have a convex function, life is much nicer, and there is a rigorous proof, mathematical proof of why convex functions. So the convex functions are defined by the fact that the line segment lambda y plus 1 minus lambda x, this is a line segment, the function should always be lesser than the line segment joining that, right? I mean, the value of the function should always be lesser, and that's given by this equation. And a rigorous proof of it can be given. It's a very simple proof. It's not a complicated proof. You can go over it, okay, on why for a convex function the global optimum is a local optimum, right? And that's a neat little proof. But yes, so I mean, ultimately, if you take the point that be it logistic regression or Poisson regression or whatever regression, it's solved through the maximum likelihood, and which ultimately uses some of these optimization techniques to find the minimum, to find the probabilities. Okay, so this is the mechanics under the hood of the solution of certain modeling problems. Okay, and I think we would we can close here. So next week, as I was telling you, it is going to be a workshop on modeling. Okay, you are welcome to work on the classwork or even work on your project, and I would be there to help you on some of these things. Okay, and the week after that is a presentation. So officially, my boring lectures are over with this, and we can yeah, meet next week. Thanks.
So I have some questions related to my